So I welcome Dr. Harpreet Singh ji to start the second session. Please.
Okay, thank you very much. So, next session. Now, I would like to ask the audience if they have some questions right now.
I think, sir, we will take question answers at the end of talk
Okay,
that
so
we
let
have.
me know this week. 9:15 we will start with the session of questioners. By 9:30 will end.
Yes, sir.
Okay, more time on this. What I have to show.
Yes, sir.
Well, let us talk about some of the applications of code spray, right? Now, this is the one study which I want to show here to our audience that we develop these coatings in house, which is nickel chromium based coatings. Now, these nickel chromium coatings basically they work very well for power plant boilers. No, the boilers, if you see, I'm talking about the water tube boilers. So you might know that these boilers they are subjected to what you call hot corrosion, high temperature corrosion, and erosion. Now, when we all know that our fuels somehow have these sulfur and the sodium and all that stuff. And when the temperature of these boiler tubes increases, I'm talking about fire side of our boilers. So what happens is that the oxide layer, which typically generates on nickel chromium alloys or whatever steel we are using, chromium based layer is there, which is protective, of course. But what happens is that these salts they make sodium sulfate or ammonium pentoxide type of salt deposits on these boiler tubes, which will then act or react, I would say, with the protective chromium layers which are formed on the boiler tubes, and hence they will flux them. In other words, there is a loss of oxide layer which is protective, and our system executes what we call corrosion or high temperature corrosion, which if is not stopped, it will keep on you know leading to the degradation of the boiler tube um, wall, and one time it will happen that all of a sudden the thinning and hence puncturing of these boiler tubes can happen. So this is one thing which happens, which we call high temperature corrosion. Another thing which happens is, when this fuel will burn, so you will have some fly ash particles which are going up, right? And these fly ash particles are having some harder phases also, which will impinge on the boiler tubes, and they will also erode the boiler tubes. So you get erosion also. So this combined thing, high temperature hot corrosion as well, or high temperature corrosion or hot corrosion, what we call usually, accompanied by erosion, causes a lot of damage to the boiler tubes. So the remedy here is that we usually apply some coatings on these boiler tubes, right? So we have some cheaper material as the substrate of the boiler tubes, and on that we add some highly corrosive and erosive resistant material on those boiler tubes. So this study is basically about that. So if you see, we deposit these nickel chromium based coatings on the boiler tubes. So we developed so many different application, different types of compositions. If you see, we added this harder phase also, titanium carbide, in the nickel chromium matrix, right? Just to have more erosion resistance also. And we added rhenium also, which is a rare earth element, which can help us to, you know, make our oxide layers more intact, and growth rate of those oxide layers can also be controlled. See, the beauty of oxide layer on one side is that it can arrest the corrosion, further corrosion of the substrate material. Suppose we have a material in steel. If you put it into, say, corrosive environment, it will develop a protective oxide layer on it, right? But the problem happens when this oxide layer growth is not controlled. So especially when temperature is increased, the thickness of these oxide layers keep on increasing. As the thickness is increased, the adherence of that oxide layer with the substrate is loosened and it loses. The oxide layer goes away. Now, this is especially true when we have the fly ash particles also, which are further, impinging on these oxide layers and making them fly away. So all this mess has to be stopped. So for that, we have introduced this harder phase into the coating. So the good thing is that we can deposit very nice thick coatings on our boiler tubes. If you see the cross section of this boiler tube material, this is the substrate, this is the coating. You see how dense coating we have produced through cold spray process, right? So you can see this is what we call mapping, EDS mapping of various elements. Usually those who work in coatings, they would do these kind of analysis. This is a cross section of that sample which shows the coating as well as the substrate, and then these are distribution of elements. See how intact chromium is introduced, and nickel and all that. And mind it, this micrograph is after exposure to erosion corrosion. So how did we do that? This erosion corrosion test was in fact done in the boiler itself. So we took these samples and we hung them into the boilers at locations where this erosion corrosion phenomenon is very severe. And then after exposure of 1500 hours, we took them. And you can see how intact still these oxide layers are, or these coatings are still with the substrate. In fact, we checked the weight gain, which is one of the meters just to check whether oxidation has taken place or not. Another thing is coating thickness measurement, right? We have made coating thickness measurement lost. When we will hang the samples in the corrosive environment, corrosive and erosive environment, the corrosive and especially this erosive environment is basically uh, uh, flowing parallel to the flat surfaces of the rectangular samples, and in doing that it will erode the our samples and hence cause some thickness loss, right? So what we have done, we have calculated that thickness loss after 1500 hours, and here you see the results. You see this uncoated sample was also hanged, and then the coated samples were also hung in the this manner. You can see the clear cut effect of these coatings, right? So this is one study which we conducted, and you can see the success of these coatings from these micrographs, that nothing has happened. Not even any kind of oxide has formed, significant oxide has formed inside the coating. Coating is called to be successful if it can first retain its own elements. That's one thing. But if second thing is, if the oxygen is not penetrating towards the substrate, which is not here happening, right? And all that. Similarly, another study which we did, this is done by in fact Dr. Manoj Kumar is another PhD student. So what here was done, basically we have developed here nanostructured coatings. So here the structure of these coatings, the grain size of these coatings is in micron size, but then here we have reached to nanostructured coatings, basically by playing with the powder chemistry and morphologies, right? So there was a strategy that we made this powder, and then we this one. In fact, this is very innovative work. You know, let me give you an anecdote that one of my colleague in chemistry, Professor Narendra Singh, and I was talking to him that he said they are extracting nickel and chromium from the industrial waste, sludge, pickling plant sludge, and so on. Then I said, this is a great thing. If you can recover that nickel and chromium, we can make nickel and chromium powders, and then we can deposit them on the boiler tube steels and see whether we are getting some benefit or not. So this is what again what you call sustainable thing, recycling the waste and all that, right? So under that mandate, this work was done, and we could develop again very nice coatings. By, of course, we could not deposit 100% waste here, because that waste was the recovery from the waste of this nickel and chromium was in the nano size, so it was difficult to move through our powder flow, uh, you know powder feedstock, sorry, what do you call, our powder feeder. So but we added that some fraction, 10%, 20% of that recovered powders from the waste into the new powder, right? At least some fraction we are saving of the fresh powder to this thing. And again we then characterize them, we tested them in the actual boilers and all that, and we could again see very nice benefits of these coatings. Um, Another thing which we did here was that we even compared how our coatings are, our cold spray process is placed वैसे with the high velocity oxy-fuel process, right? And we see here clearly that our nickel chromium coatings developed by cold spray process were better than this one. This one. This is another work which I was quoting, that here this work was done for Institute of Plasma Research. So they are developing this fusion reactor. So their requirement is to deposit a very thick pure copper coating actually. When I say thick, they want 3 mm thick coatings of copper, right? And that has to be pure, because their purpose is not for corrosion or any other thing, but they are using these coatings for passivation of plasma currents, for which they want very good thermal and electrical conductivity in the copper coatings. Now, this was a magnanimous task, that 3 mm thick deposit of pure coating has to be, pure copper has to be developed, right? So then we took it at IIT Ropar, and with, of course, with the help of our IPR, the funding, and then we could deposit these coatings, right? It was a challenge actually. The copper, first thing, it has to be pure. Another thing, it has to be deposited on stainless steel, which is a hard material, right? So copper on stainless steel, this was challenge, how to get a good adherence, right? That was the one research problem, because when we deposited on the as received um, substrates, we were not getting very good you know adherence strength, because one of the worry of coating engineers is how well the coatings are adhered to the substrate, right? So we have to do a lot of work in terms of getting required adherence strength with the substrate. For that we played extensively with the surface roughness of this substrate before coating, right? So we have to optimize, I should not say optimize, but we have to come up with the different kind of strategies to get this, I mean, different types of reference levels to get uh, and a better adherence on this surface. For example, here we used as received as well as semi-polished and mirror polished samples, right? And we were amazed to see that in this particular case, we got very good adherence for mirror polished uh, samples. This is another thing about cold spray. In certain cases, it is good to have some roughness, but in certain other cases, it's good to have a mirror polished. Whereas in thermal spray processes, it's well established that if you have a required roughness, in fact, roughness is the driving thing there because there is only mechanical keying effect. But in this case, you have our requirements of surface finish change as we change the set of materials, mean material to be coated and the powder material, substrate as well as the powder characteristics. When they change, the roughness requirements also change. So in this hard on soft contact, we saw that mirror polish is working well. Why it is working, I'll come to that also. Working well. So when we deposited, we could get the adherence strength and everything, but still electrical conductivity was a challenge, which was of the order of which was required to be of this order. So for that, what we have to do some kind of heat treatment, as I was telling you. So this is as coated, and this is after heat treatment, right? So we could see that after heat treatment, we were having better thermal conductivity and electrical conductivity and so on. So another thing which we were, of course, we uh, kind of, uh, characterize it very nicely, and even 3 thickness was also achieved, right, which was one of the objectives. And another strategy which we tried in this work was also that to improve. See, why I'm telling you all this, because adherence is a big challenge. So one strategy is that if you are playing with the cold spray coatings and you are facing a challenge of adhesive strength, so what could be the possible strategies? One is to play with the surface roughness of the substrate prior to the coating. Another thing which we did in this project was we introduced an interlayer, very thin interlayer of copper, and in one case chromium and nickel through electroplating also. So that on the steel we prepared one more some very thin coating by electroplating, and then this thick deposit of copper was done. That strategy was also helping us to get a very good adhesion. So different types of strategies can be used. Uh, this is just to tell those who want to explore this technology, right? So this is another. This is not my work, but our work. But this is from some literature. Just to tell you that, see, copper coating on different polymer substrates are also possible. So see the capabilities of cold spray process, right? This is done at IIT Ropar. This is copper ring made on a polymer, which is PMMA polymer. We have deposited this coating, right? So this kind of work can be for some making, say, some electrical circuits on certain polymer substrates and so on, right? May stuff like that. This is another study where electrical conductivity of CS 10 copper composite coating on polymer substrates have been made. So see how nicely, because you know why I'm telling you again this, because polymerization, sorry, not polymerization, the metallization of polymers is a quite challenging task. But nowadays we have quite a few applications where we are looking for coatings on these polymer substrates. In fact, the biggest challenge is still there. Those who want to research is depositing coating on pure polymer is fine, but depositing coatings on CFRPs, what you call carbon fiber reinforced polymers or plastics, is again a very challenging thing. But there's a lot of market for it actually. In drones and all that, several applications are there where we are using these CFRPs. But these CFRPs have to be coated with some metals for some kind of functionalities. Right? We are also trying this work in our lab. In our case, it is basically we want to save this drones which are made by CFRPs from laser attacks, right? So we know that these directed energy weapons are of the future. They're coming up. So enemy can use that laser gun to annihilate your say drone, right? Now the CFRP is prone to this laser attack. So what if we can deposit some ceramic coating on that CFRP or some other reflective material on those CFRPs to mitigate or at least reduce the risk of this laser attacks. But the challenge lies how to deposit coatings on these CFRPs. So we are trying, but those who want to do some research, this is a good problem to do. Actually, I suggest you can try this through any route. Actually, not necessarily through thermal spray, cold spray, but still not much success has been achieved to deposit coatings on CFRPs. There are some other studies where cold spray has been tremendously used. So we have this bond codes for TBC. TBC is one of the most challenging coating application, which is thermal barrier coatings on our gas turbines, right? So gas turbine engines like your aeroplanes and all that. That's a big problem there that you want to, uh, you know, save your turbine blades, gas turbine blades from your heat, right? The extensive heat which we are producing in the combustion chambers of these gas turbines. So there typically we use thermal barrier coatings, and the architecture of these thermal barrier coatings is that usually we have the superalloy blade on which we apply some bond coat, which is typically metallic, and then we apply the ceramic coat, right? Now there is a challenge in having a lot of research is being done how to achieve kind of good properties in bond coats as well as these top coats, right? There's a problem of life, there's a problem of colds, sorry, these hot corrosion and all that, right? A lot of research is being done, and cold spray has also been tried in these kind of applications, right? Another material which is very favorable to aerospace is titanium based coatings on these aluminum based alloys, and you can see very nice coatings have been developed by, again, it's not our work but is from literature, that you can deposit. See how beautifully these coatings are being made. Biomedical applications, as I told you, lot of market is there, um, and so many types of coating techniques have been used. So is the case with cold spray also. People are trying. For example, this is a porous titanium coating by CS. So see here, I was talking to you that cold spray can be used to tailor the porosity. On one side, we are depositing such thick coatings, but on other side, we are depositing these coarse porosity pore coatings, because in biomedical, usually we are looking for pores coatings, right? For this better cell integration and growth and all that, right? So you can see different types of materials have been deposited. This is some work which we have done at IIT Ropar also. And this is about depositing these titanium and Baghdad coatings, right? So Baghdad is a promising material which can replace our most commonly used material, which is hydroxyapatite, which resembles our bone. But the problem is in HAP is that it has lesser mechanical strength. So by chance, Baghdad matches also very much matches with the HAP as well as bone material, because it's again a calcium based, but it has some zirconium which makes it mechanically better also. So that's why we wanted to explore this material as a replacement of Baghdad. and here, sorry, as a replacement of HAP, and we develop these coatings in house uh, through this. So you can see these coatings being deposited with different fractions of our Baghdad and so on.
Hello.
Dr. Harpreet, sir, you has been muted. Please unmute yourself.
Somebody else has muted me. Hmm. Am I? Hello?
Yes, sir. You are
Yes,
audible
yes,
now, sir.
How long I was without, voice?
for a
I,
minute or so.
Okay, that's fine. It's otherwise it was like I don't know. I have not done it, but somebody else has done, or I don't know what happened.
It's okay, sir. It's okay. Fine.
Am I okay now? Yeah, okay. So so a lot of I was telling you electrical appliances. So electrical appliances also need coatings, especially this copper and composites of copper. Even where we want very high thermal conductivity, I can't disclose you. We did one project with the ABB. They wanted silver coatings, right? All those applications are quite feasible by cold spray, right? Because other techniques we have a high temperature and you get damage to those temperature sensitive materials and so on, right? So nuclear windmill energy generation applications. Nuclear is again industry where they are looking for high pure coatings. In fact, we are doing one project with the park. Again, I can't disclose what the details, but our atomic research, we are developing some coatings for them for this accident tolerant fuels and rods and all that. So lot of applications lies still there for cold spray. Then coming on to some case studies where cold spray has been used for additive manufacturing. See, when I say additive manufacturing applications, so since cold spray, we have already understood that it can deposit very thick coatings or thick deposits, right? So two aspects it has been used. One is to deposit to kind of manufacture standalone parts. Second is repair. I'll show you some case studies here. For example, this is freestanding by material hollow shape permanent magnet fabricated from this complex materials, right? Using cold spray based additive manufacturing process. This is also multi-material type of component which is again made by this is a hollow cylinder. But please remember, all these are used mostly for high end applications, not for say hanging your fan or something of that, right? So this may be in aerospace, this may be in nuclear applications or transportation and all that, where risk to lives and where we are looking for very kind of high performance components and so on. Similarly, here you see how thick copper inner wall has been made on um, this food processing machine, right? So here again, the chances of oxidation and other things can be avoided. And here again, some components, aluminum alloy tube, aluminum flange, and so on. Here, this is a rocket nozzle by Impact Innovation. This is again made by Cold Spray. This is a very high-end nozzle for use for space crafts and so on. Um, the conventional technologies, they take a lot of time actually. I think more than 2 months to make one nozzle. But this has been made by Impact Innovation, I think, in 40 hours or so, which is tremendous actually. So this is again one of the longest case studies which endorse the use of cold spray based additive manufacturing. This is again some flange. Whole flange has been made by, this is 50 to 60 thick deposition, right? See, this has been entirely fabricated by cold spray. This is about repair aspect, which I was telling you. See, these all are aerospace parts, which are very costly. I have seen people, you know, at least one when we talk about gas turbines, so there each of these blades they cost millions, uh, right, of rupees and so on. So it's very difficult to kind of replace them, right? Very not very economical thing to do it, right? So cold spray has now provided us the facilities that if these components are damaged, usually they are damaged by erosion and all that, right? So small pitting is done on is there on these components, which further leads to some kind of loosening, and uh, we lose the tolerance, the required tolerance and allowances. Due to that, we face some functionality problems and vibration and all that. So cold spray, as we know that you can take the powder and deposit it in the almost pure form, right? So suppose this is made of mild steel, so mild steel powder can be deposited on it, right? Without any oxidation or something like that. Deposit and then refurbish it, and you get a as new as part. You can see here, right? So you save lots of money in these. All these are some of the applications. See, this is a nose wheel steering actuator barrel. So this again some aerospace. So you can see how well it has been replaced, or sorry, repaired. Here again, this is a damaged part. This has gone. So they have done cold spray here, and then they have machining and hole has been made. So it is again a fresh part, which can, I mean, again, workable part for aircraft, right? Similarly, these blades, right? And you can see these cone structures. This is another very interesting application. You can see this video also, I think, available. So this supply gear has been made on this integral with this shaft, right? Uh, Hollow shaft. So through cold spray. So basically, the trick here is that how well you can manipulate the relative distance, relative motion between the workpiece and the gun. This is the gun, right? So and so on. Some more examples of this repair work you can see here, right? All this restoration has been done. Even cold spray has been used for joining dissimilar metals also through different strategies, right? For example, this magnesium based two components have been joined by cold spray aluminum and then machined, and you get this. So another thing is that these kind of polymer on this copper has been deposited on this, right? So all these interesting applications are can be seen. Then a lot of research in terms of 50 thick copper coating on aluminum, right? And of course, then this is more towards researching it, like people analyze single sublets and so on. There's more deeper studies, right? but you can see this capabilities. Pure tantalum deposited by CSN. So this you can see this much 5 mm and so on. So similarly, this oxide dispersion strength and coatings. So you can see copper with aluminum oxide. So we're talking about the composites, right? So this is, see how thick, 16 mm. So these kind of components have been deposited. This is again pores tie 64 for biomedical applications. So this one, this is a highly reflective aluminum coating which has been deposited. So this one. So functionally graded. So another lot of interest nowadays in functionally graded materials using. So you can then grade these materials, right? We have this SLM material. Then on this we are depositing copper by sorry, aluminum composite by cold spray, right? So we are clubbing our conventional data manufacturing with our CS and so on for different functionalities and so on. This is a work which we done at IIT Ropar. We deposited very thick nickel chromium deposits, right? Even titanium we have also deposited. Then we characterize them actually extensively. We characterize them and we benchmark these plates, we should say, deposits versus their as cast uh, materials. For example, what I mean by that, that for example, we have made this plate of titanium by cold spray. Then we took another one which is commercially available by our casting route, and then we compared their properties. And we was surprised to see that even the properties of these, we extensively characterize them in terms of their hardness, their tensile strength, their nano hardness, and all that, and of course cyclic oxidation behavior and all that. So we can go, we saw that the properties of these materials I mean made by CSM, they were equally good as or equally comparable to their uh, as cast titanium materials. This is another aspect which I want to touch. Those who are good in simulations, as I told you earlier also, that it is very difficult to monitor this process experimentally. So the whole bonding mechanisms, etc., they have been understood basically through simulations, right? So simulation, still there are a lot of scope that we can simulate things. We can understand this process for different set of materials. Okay, we can use it for parameter optimization also. For example, as I told you, we end up spending a lot of gas. For example, this is a relatively new process. We don't have database for several material combinations. So as soon as a new material combination comes to us, we usually feel worried, and we have to spend a lot of gas on making some trial and error experiments, right? Now the better approach. One of my students, Parminder, has just completed his PhD. He simulated first. He arrived at certain optimum parameters through simulations only for his titanium, sorry, his work on superlies. So first he arrived at certain parameters. So this much pressure is needed, and this much velocity is needed, and so on through the simulations. And then he did the experiment, which saved a lot of money actually, right? So this is a one thing which is still there, and a lot of work can be done in that. Similarly, other aspects can be correlated. Residual stresses, right? How much residual stresses you can you predict them, right? And stuff like that. Even prediction of deposition efficiency, critical velocity, and all that. A lot of interesting things are there. Still, there is a scope. If somebody is good at this simulations, especially abacus or these uh, um, these fluid mechanics what you call CFD simulations and all that. It's good. It's a great learning actually. So this one. So how do we see this cold spray in context of Dusty 4.0 frameworks, right? So the aim here is that still those who want to work in this machine learning and AI stuff. So there is still need actually that one of the challenges is that it's very difficult to monitor the deposition process online actually, right? So usually we say uh, spray and pray means कि भाई एक बार डिपॉजिट कर दिया देखते हैं क्या निकलता है then you have to see that deposit, you will bring that, you will cut it, you will analyze it, maybe after 1 month you will come to know that whether it was good or not, right? But here the dream is that if we can have certain modules which can online monitor the coating built up, right? So inter-process modules, uh, reward modules, post-process modules, in situ measurement module. This is what I was talking to you. So if all that can be clubbed, right, or integrated, that will really give us a kind of industry 4.0 compatible uh, cold spray system, which is basically uh, needed, and those who are interested, they can also think about doing some kind of research. uh, Even right now, if you can have some kind of feedback loop here to see the built up online, right? And if you're not getting say required cohesive strength or something, you may have some kind of feedback loop and to tinker with the parameters and so on, right? And maybe machine learning can also be used in one way to other to if you have a lot of data, so you correct this, right? Especially when you keep on depositing very thick materials, there is need to change these parameters accordingly, right? Because the standoff distance keeps on changing, right? So a lot of those kind of challenges they need to be settled, uh, especially in an autonomous way, what you call 4.0, right? So those are the things, right? Now, this is anyway, I think this is the last slide in this presentation where I say because this cold spray system or cold spray facility is a national facility, let me tell you, and you can use it. You can use it. We have different financial models to use it. One is you pay and use. We can give you consultancy also, or we can do some co-development, and we can write some proposals also, national, international. In fact, we already are doing some work with national and international universities and so on. Even we keep on doing hands-on training also. Last July, we conducted one full week training on this. Next July again, we will plan one more, and even we have one. You know, we are going to have one day workshop also in the month of say January end or so. You can keep watching our LinkedIn page and so on. Anyway, leasing out, etc. This is for industry. So, I mean, what I want to say here is that this is a national facility, and you can think about using this cold spray for your search also, and we are open for that. So, thank you very much indeed. So, this is one aspect which we can talk about. Uh, we have 10 minutes or so. I can show you some more work if you wish. which is, although I have so many presentations here, but let me show you here. This work was very much acknowledged. So this was, I was telling you that these coatings, right? These, this is the fusion reactor actually, uh, nuclear fusion, and these are the triangular plates on which we wanted to deposit these coatings, thick copper coatings, right? What I want to now, the challenge here is the how to achieve the required adhesion strength. That was the whole big challenge in this, because we have a stainless steel on one side and other on it we have a copper. So there we tried different types of strategies actually. So I want to show you here that how did we achieve this this effect of surface roughness. So I told you that we tried two strategies. One, in one case we played with the surface roughness. Now we saw that in case of mirror polish we got a very good adherence. Now the question is why it was coming out, right? So that was the thing, and that was cleared by this single particle impact studies. Why I'm showing you? Because I'm telling you that how to go deeper into something, right? So, well, we tried three, as I told you, three roughness levels on our substrates, but in this mirror polished we got very nice mirror polished finished samples. We got very good adhesion strength. So then we want to understand. So for that, Surinder Singh, my PhD student, he did this study with single particle impacts. Now, single particle impacts, they give us a lot of good information. For example, here you see in the first where the roughness level was as received. So you did not, you although are getting some kind of, this is single particle, this is single particle, this, and here again, but here you see a very nicely whole of the particle has gone inside the surface. This is substrate, this is the particle. Again here we have some kind of hindrance to the whole penetration, and the particles even remain undeformed, right? So so this gives us some idea that it is basically the plane surfaces, they are giving us a very good kind of passes to particles to go deeply inside and have a full penetration and have this jetting outside here. This is the jetting. So we are seeing from the top. Earlier pictures I will show in the previous lecture were from the cross section, right? So you can see it. But this is the condition where no bonding was taking place. See how nicely he captured this SCM picture. So for this you have to spend a lot of time on SCM. So he saw that why the bonding is not happening in as received thing, because there was hindrance to the movement. This is the copper supply, this is the substrate, and these are the hills and valleys on the surface. Although they are getting deformed, but still there is a gap actually between these particles, right? And and I was talking to you that how to see whether the particles have gone deeply into it or it is up on the surface. This is the substrate, this is the single particle in mirror polished, this is as received, this is semi polished. So how to get information from SCM? Sometimes it may be skeptical. So what he did, he did the profilometry of these things, right? From the profile he could see that for this he could get an almost straight line. That means the particle has gone much deeper into this thing. But I was telling you, no, this is the second case where we have semi-polished. Even in the semi-polished, these are the hills on the surface. Although the particle has come with a lot of energy, but lot of energy has gone into deforming this only, instead of having this energy going inside, entirely inside the surface. But now you see the last one here. When we were having this Mineral pause thing, there was nothing to hinder the movement of this copper particle into the substrate. And you can get very nice endurance. Now, from this, you maybe it is not wise to say कि यहाँ पे we have a copper, this is aluminum. So that is where he took this EDS. From EDS, he could easily see that this is copper and this is the substrate, right? And you can see how nicely the jet formation has been seen and all that, right? And the copper particles quite sitting, penetrating inside the substrate. So why I'm showing this? Because sometimes it's good to go into deep and to have good publications, right? So no hindrance due to surface asperities and so on. So he could get this one, right? So these kind of studies. This is another. I was telling you that electroplating how it can help in certain cases. Although we achieve the target through electroplating also, but we did not recommend it as final because the electroplating means we are adding one more kind of step in our final thing, right? So which is not a great thing to do. Again, here you can see this actually nickel electroplated substrate helps us very nice here to have copper supply. So, okay, so there is copper electroplated substrate could not help us, and we were having this one. So this nickel being having good strength is did not get damaged, but copper electroplated layer got damaged when we uh, place the copper supplat over it by cold spray. What does it mean? Means if we have to recommend the right way of adherence, achieving adherence in by this electroplating route, we will say we need a very thin electroplated nickel layer before we deposit the copper, but not copper over copper because copper does not have the required strength, electroplated one, and it broken away. And again, we did not see the uh, right bond here. So these are different types of studies. So we can keep going on and on because, as I told you, so many students have done good work on all this. I was talking to you on this Baghdad coatings. So you can see one thing I want to show here, the laser effect, right? So laser remelting actually worked very nicely. Actually, it helped us to improve only slightly the above layers only. Right? So you can make a gradient in terms of because sometimes it's not economical to or even not required to you know uh, treat the whole layer one thing, right? Another danger sometimes is uh, the laser treatment helps you, as I told you, to control the depth of the heat treatment. But when we do the overall heating, the conventional heat treatment of your samples, the chances, or in fact, the problem is that in that case, there is a diffusion also between this coating and the layer or the substrate, right? Which is nicely can be avoided by controlled laser treatment, right? So which he demonstrated, and of course he got some other benefits in terms of grain refinement and all that. So and then he tested these coatings under several environments. I think let me stop here and let me have some questions if there are any. So we are almost 15, 18 minutes for that. Thank you very much. Yeah.
Thank you so much, sir, for your wonderful talk. Now,
Again,
I would like all participants to join the conversation, and if they have any query, if they want to ask some question, please go ahead.
unmute yourself first and then ask your question.
Sir, send me PDF.
Uh,
Unmute
Hello,
yourself.
hello.
Hello, Jeff sir. Send PDF in the WhatsApp group.
Yeah, we will try actually, but see all this
I think
whatever.
these, sir, I have answer. These lectures are will be available on YouTube, so you can go through those lectures. I think if sir will share only, then we can share you the PPT.
Yeah, actually, it will be difficult to share all this. There is some information which I would like to avoid, but if you go through our literature now, as I told you, every most of these things are published actually, and you please, if you want those papers, we can share those papers with you. Na?
So
You
we
can
will share
Google.
the Google link, the YouTube link to the participants after this. Tomorrow we will share the link
Yes, sir.
of this talk.
Can you please share the links of YouTube as well as the research papers which you are consulting on
Sir,
this
YouTube
Yeah.
we
sandbox?
will share tomorrow. YouTube link we will share tomorrow. You will get the
Okay, sir.
links.
Okay.
Any other question?
Sir, I have one question regarding thermal coated materials.
Mhm.
So, how can I check the thickness of the coating? Is there any non-contact type of a system for measuring that?
Yeah, there are, but best way to measure the thickness, because especially, uh, you know, we have slightly, I mean, thicker coatings in our case. So we use basically vernier calipers. They help very nicely. But yes, there are some non-contact type of systems also, by which you can measure based on this ultrasound and all that. But best and tested one is this: you measure it by verniers, at 3 4 places, and then take the average. Another thing is that you would like to verify also. So for that, you can uh, use later on the destructive method. That means you cut the sample, heat under microscope, or and then you uh, kind of verify it, right? So yeah.
And sir, what is the significance of nano level surface finishing for the coated materials? Uh, should nano finishing require for that coated materials?
No, 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 not nano actually. So see, as an engineer, you should always think about economics of the overall solution, right? So why, you may always ask, for example, this copper work, we started with as coated itself, sorry, as cast material, because if the things work with as cast, nothing like that, right? But then you go with slightly more finishing, I mean RA value, so you can reduce it, right? Then you further reduce if nothing works, right? So nano, I would never say, because nano is not going to help you. It's only micron size of fish which we have got. In fact, in certain cases, roughness is helping us. As I told you, in certain set of, uh, I will require you to read some literature on uh, different types of contacts. For example, due to lack of time, we could not discuss. It makes a lot of difference in terms of surface preparation when you are talking about hard on hard coating. Hard on hard means hard substrate, hard material, coating material, right? And there is another set where hard on soft, or soft on hard, or hard on hard. So in all these cases, in certain cases, your roughness helps, right? Roughness helps. For example, you have a very hard material and you have very soft material on it, uh, to be deposited by cold spray, right? So in that case, if you have hills which does not deform at all, and your material is very soft, say zinc or something of that sort, that will stick very nicely on it. The problems comes when in our case, for example, in Surendra's work, what happened? The steel hills were not that much rigid that they are not sustaining. They were not sustaining that load. They were like deforming partially, right? So if the material is very hard and your material to be coated is very soft, the hardness will help. Sorry, the roughness will help in that, right? So nano finishing, I don't think it will help in any case actually, because it's a costly affair. Nothing we need not to have actually. It's only micron size things will work nicely most of the case.
Okay, thank you, sir.
Mm.
Any other question from the participants?
Sir, am I audible?
Yes, sir. Yes.
Yes.
My name is Venkat Rambabu. I'm basically from civil engineering background.
You're
Sir,
from?
I am from civil engineering background, sir.
Okay. Mm.
Just I want to know the materials which can be used for protecting the steel against corrosion, which are in underwater.
Yeah, underwater. Okay.
Yeah.
So underwater, actually, even our steels are doing good actually with the high
Yes, sir.
chromium content. They are doing nicely. Even aluminum-based coatings, they are helping us a lot actually. And underwater, we have very famous material which is nickel aluminum bronze, which is usually used for our this all ship equipment, right? The propellers and all that. So there we use this nickel aluminum bronze material, which works very well. Those kind of materials are good actually. Hmm? So
Thank you, sir. Thank you very much.
Anyone else would like to ask a question?
Good evening, sir. Can you hear
good
me, sir?
evening.
Yes,
Yes.
sir.
Yeah, sir, I am Dr. Shanmugapriyan from Kanyakumari, sir. Kanyakumari.
Oh, nice.
Okay, sir.
Very good.
Yeah. Uh, sir, my question is regarding the thermal spray coating. Normally, the thermal spray coating using the powder is alloy normally. So the alloy having different melting temperatures. So how to fix the temperature for combustion of temperature in the thermal spray coating? And if a powders is some powders are purely melted, some powders are unmelted. If you isolate the powder to deposit in the target of the substrate, if the target of the material having some unmelted particle, if you the coating of entire component is quality or any the quality will be significantly reduced, depends upon the acid rate of the powder is target material. So please give me suggestions about that, sir, please.
See, there are two things. What if I understood correctly? See, one thing is that it's not possible that you mix nickel and chromium and deposit it on the substrate and you will get nickel chromium alloy. No. First thing is, to get alloy coating, you have to use the alloy powder itself in thermal spray, right? There is no mechanism in between that which can make different powders as an alloy. One thing. Second is, we have now a lot of database for these temperature settings for or what you call process parameters for different types of materials, right? So you have to refer to that. For example, it will depend. If you are trying to say nickel chromium alloy powder you want to deposit, you will get a lot of data that what kind of pressure and these parameters of say HBF or detonation gun or thermal spray has to be fixed. But if the material is entirely new to you, then only two things can help. One is you simulate it, the process, right, which is one option. Second is you try to see a similar kind of materials in the literature and work out some range of parameters, and then you do some hit and trial experiments. So those kind of possibilities you have to explore, right, for newer materials. But fortunately, except cold spray, most of the processes you will find some kind of parameters, some kind of recommendations, even standard data books, uh, which will give you range of parameters for different materials. Fine? Or you have
Okay, sir.
something else
Thank you.
to?
Yes, sir. Okay, sir. Sir, what about the porosity level of when we apply the heat treatment processing? What is the solid solution strengthening of nickel chromium alloy compositions of which material? So, how to reduce the porosity of behind this? Anything?
Yeah, actually, if you unfortunately I could not tell you, but we have used hip treatment actually in our work. I showed you very thick deposits, no? So there the porosity problem was tackled by hot isostatic pressing, method. Uh, and there we could reduce the porosity to a larger extent. Although it was not zero, but still, I think it reduced by, I think it was 5%, then reduced to 1% or something of that sort. So hip is one process, then you can do this. Of course, normal heat treatment sometimes helps, but then there are some in situ uh, strategies also. No, I showed you that in situ hammering thing that helps actually both way. It reduces porosity as well as increases the interlaminar uh, adhesion also, right? But then lot will depend upon the parameters also, no? So yeah.
Okay,
Anyone
sir. Thank
else?
you. Thanks.
Anyone else who would like to ask any question?
Hello, sir. I'm Dr. Gurpreet.
Yes, hello.
Sir, I want to one question. Sir, can we apply the thermal coatings after the polishing processes?
Yes, yes, we can do.
Okay, thank you, sir.
Yeah. So if it's a requirement, then you can do it. But the thing
Okay, sir.
is that, for example, why you would like to polish it actually if you want to have another layer on it, no?
Yes, sir.
So that polishing or whatever pre-treatment you want to do on your substrate is basically to have, if at all you want to use coating, so you have to tailor it according to the coating requirement or process requirement itself, right?
Right,
So
sir.
yeah.
Sir,
Any
I asked this question because my area is polishing. I'm from
Mhm.
mechanical background, so that's
Mhm.
why I asked this question. I'm using the magnetic resist finishing process for
Mhm.
polishing the materials.
Mhm.
So that's why I asked these questions.
Yeah, actually, see, the thermal spray or cold spray does not need that level of polishing. So, for research sake, you can do it, but economics will not work, right? So, in
Okay, sir.
fact, I will, if you want to extend your work now, try your process on already sprayed materials, because there is a lot of scope to investigate processes for processes for finishing of the thermal sprayed materials. जैसे हमने कहा बॉयलर पे हमने कोटिंग तो बना दी है, बट देन
Yes,
we
sir.
need some required finish on that, and it's quite challenging to finish these coated layers, because
Right, sir.
especially this cold spray it becomes very brittle, and if you have some material which impose a lot of finishing force on the deposit, it will break away. So there your magnetic uh, this thing na,
Abrasive finishing, sir.
these finishing processes must be investigated for those kind of deposits,
Right, sir.
right? So there could be a
Right, sir.
combination.
Okay, sir. Thank you for this informative session, sir.
Thank you.
Anyone else who ask
Sir,
any question?
hello. Sir, I have another one question, sir. Sir,
Please, please.
plasma spray coating is called as a thick coating, and coating is related with thin coating. Correct, sir?
Say again. Your voice is breaking. So you
Sir,
said
sir,
plasma spray.
plasma spray coating is related with thick coating type, and PVD and CVD coatings is related with the thin coating. Is that right, sir?
Yes, yes. Usually
Yeah.
CVD, PVD, na?
Yes,
We
sir.
go up to say
What about?
25 micron max.
Yes, sir. What about the difference between PVD and sputtering method of coating? Also, is thin coating, yes, sir? Sir, sputtering method.
Yes, sputtering is one type of the PVD, na? So
Yes.
PVD is basically physical vapor deposition, right?
Yes,
So
sir.
now
Yes,
this
sir.
vapor deposition you do it by sputtering or by simple heating and atomic by atomic, atom by atom you evaporate the material and get it. So magnetic, that is a type of PVD. You know, your
So,
magnetron sputtering is type of PVD.
sir, are you suggested what type of tribological testing method for applying on the coating method to testing the wear properties? Likewise, ASTM standard. For example, thermal spray coating, what type of suggested wear testing method, and thin coating PVD, CVD, what type of testing method suggested as per the ASTM standard, sir?
He the before I recommend we must know the application, right? So if it is the coating has to be used under say sliding contact, so we have to think about finding relevant ASTM standard for sliding contact, right? If it is rolling contact, it's rolling contact. So that is one thing, and if you see that you can find out. I don't remember the names of those ASTM standards, but yes, we have good information about ASTM standards on uh, testing these coated materials under different tribological conditions or applications, right? So वो तो it's not a big deal. You can always Google it, depending on the first. But the biggest challenge in tribological testing is first to identify what kind of contact you have, whether you have a sliding contact or you have a rolling contact or you have a reciprocating contact, right? This has to be taken care of first. First, from there you will come to know that okay, this is the configuration, and then you can search. But yes, this question is very valid. This is for all. Whenever you test any material, please follow the ASTM standard, relevant ASTM standards for that, if available, right?
If
Don't
you
do any
consider
testing. Hmm.
Sir, if you consider the coating thickness also for select the coating, tribological test.
I think thickness is not the issue actually. See,
Sir,
thickness
PVD
requirement
coating and CVD.
thickness will come from the requirement of the application. For example, if I want to do a coating for boiler where recommendation is 200 micron, so I will definitely go with the thermal spray. I will never go with the CBD, which can only go up to 25. So then tribological testing for that application with the CBD coating does not make any sense. है ना? So in fact, both have their own niche area, CBD, PVD. ऐसा नहीं है कि they don't have the market, but there are certain applications where they can't replace each other. है ना? That's where we have to think. But if the same application you want to test, I don't think ASTM standard will differ with this process.
Thank you, sir. Thank you so much. Very informative. Thank you, sir. Okay.
Thank you.
Mayank sir.
Haji, I think, sir, finish.
So, dear participants, we have shared the feedback link in the chat box. You please fill the feedback there. And I think this is the time to say good night. And we are very highly thankful. We are thankful to Dr. Harpreet Singh ji for this very useful talk. I think for right from the beginner to the expert, this is very much relevant for all of us. So we are greatly thankful to Dr. Harpreet sir. And in future also we will take guidance of sir.
Thank you. Thank you very much, all the participants, for listening to me. I hope it makes sense. But we are all learning from each other. So let's keep learning. And wherever I can help you, you can always contact me, write me an email or whatever. I will try to respond. Thank you very much indeed. Thank you. Good night to all of you. Thank you. I'm
Good
not
night,
logging
sir.
out.
Okay, sir. Thank you,
Thank
sir.
you so much, sir,
Bye bye.
for your kind words.
Thank you, sir.